In this video, we're going to take the ideas that we learned in the last one about this new idea of the quantum and apply the idea of the quantum to a new picture of the atom that was emerging early in the 20th century that was put together by Niels Bohr. So let's study that. We're going to first of all talk about some of the assumptions that Niels Bohr made about the atom and just look at them written down, and then afterwards we'll look at an animation and see how this all works out. So first of all, Niels Bohr said that all forms of energy are quantized. That's the idea of the new quantum theory he's applying to the atom. And what that means in an atom is that electrons can gain or lose kinetic energy only in fixed amounts. So that's what it's like to apply the idea of the quantum to an atom. And the amount of energy that electrons can gain or lose is called a quantum, or plural would be quanta. He also said, this is what it also meant to quantize an atom, that electrons in the hydrogen atom can't live anywhere. They can occupy only certain specific orbits of a fixed radius and no others. So he changed the atom by saying electrons can't live anywhere. Electrons can only live in certain specific orbits. Now in this atom, the electron can only jump from one orbit to a higher one by absorbing a quantum of energy in the form of a photon. So if photons of electromagnetic radiation hit the atom, when a photon of the right amount of energy hit the atom would absorb it, and an electron would jump from one orbit to a higher one. Now, each allowed orbit in the atom corresponded to a specific amount of energy. That we'll see that in a moment. The orbit that was nearest the nucleus represented the smallest amount of energy that the electron can have. And that amount of energy was called, that energy level was called the ground state. And he said that electrons do not lose energy when they're in the ground state. So now we're going to see an animation of the way that Niels Bohr thought that the atom worked. So first of all, this illustrates a couple of his ideas. First of all, this little blue guy here is a electron, and he said that the electron in the hydrogen atom can occupy only certain specific orbits. So these white dotted lines are the specific orbits that the electron can live in, and that he said electrons cannot live in the space between these dotted lines. So you could have an electron here, and you could have an electron here, and here, and here, and here, but you can't have it anywhere in the middle. Now he also said that an electron could jump from a lower energy level like this to higher energy levels only if the atom absorbs energy in an amount equal to the difference in energies between two of the levels. So let's watch this animation and we'll see some of these ideas at work. So what you're going to be watching is, first of all, you're going to see streaming onto the atom all these little colored circles, and they represent photons of different frequencies. In other words, different colors, different photon frequencies, different photon energies that are hitting this atom. And some of the photons have an energy that's just right to make this electron jump from a lower energy level to a higher energy level. And you'll be able to see the energy level by this counter number down here. Now when the electron jumps back down, you will also see that the electron will emit or release a photon. So let's watch the animation through first, and then we'll pick out some of these important details. Okay, so now first of all let's watch. Electrons in the ground state, and then the first photons come in, and notice that the atom absorbed one of the photons, and the electron is now in the n equals 5 level. So here's the photons, and then we absorbed one of them and jumped up. So now the electron is right here, and then we're going to see the electron jump down. Let's do a replay on that. The electron jumped down, and when it did, the electron emitted this photon. So let's continue on. So electron's in the lowest energy level, and then just the right photon comes, and now the electron is in the n equals 2 level, and the electron jumps down, releasing another photon. And so as the atom absorbs energy, and now notice the electron's all the way out here in the n equals 6, and the animation continues. The electron jumps down from n equals 6 to n equals 3, releasing a photon. And then the electron jumps down again, releasing that photon. And the process continues, and now we'll just let this go right to the end. And so now we're in the n equals 4 level, jumps down to the n equals 3, jumps down to n equals 2, jumps down to n equals 1. Now, if we kept score of the photons that are released by the atom as the electron jumped from an upper energy level to a lower energy level, we would see that because there are limited energy levels, there are of course limited jumps like 6 to 4 or 4 to 2, and therefore what we would notice is that only particular photons are released from when the electron jumped from an upper energy level to a lower energy level. Now actually some of the photons are very high energy, big jumps down, and those are in the ultraviolet range, so those are not visible. And some of the energy level jumps are actually quite small, so the energy actually is very low, so those photons are in the infrared. And then there are some jumps that the photons released are visible. And Niels Bohr's triumph of his model of the atom was that the energy levels that he had calculated, the electron jumps down within those energy levels actually resulted in the photons that had been observed in the colored lines of hydrogen going through the prism and forming the hydrogen spectrum. So he directly calculated that you should get these 4 lines from hydrogen, and the wavelengths of those 4 lines were exactly the ones that were observed. Tremendous success. So to summarize, when an electron falls from a higher energy level to a lower energy level, the atom emits a photon with energy equal to the difference between the energies of the initial and final states. So this is the formula that's on our reference tables. The energy of a photon emitted by an atom as an electron jumps from an upper energy level to a lower energy level is equal to the energy of the initial energy level minus the energy of the final energy level. And that difference in energies is equal to the energy of the photon. Now let's look at the reference tables. Now the reference tables give us the energies of these energy levels for 2 atoms, hydrogen and mercury. And what these diagrams represent is each of the orbits in the Bohr atom that we saw the electrons jumping from We know that each orbit has a certain amount of energy associated with it. So these charts actually give us the energies of these levels. So the n equals 1 level in hydrogen, for instance, this energy is minus 13.6, and the units are electron volts. And that means when the electron is in this level, the ground state, which is where the electron likes to be, you would have to add 13.6 electron volts of energy to take the electron from the ground state and remove it from the atom completely. So this represents the amount of energy associated with the ground state. Notice the n equals 2 state minus 3.4. So if I take the difference in these two numbers, which would be 10.2, 13.6 minus 3.4, if an electron is living in the ground state and a photon of energy 10.2 electron volts, equal to this difference, was absorbed by the atom, the electron would jump up to the n equals 2 level and stay there. When the electron jumped back down to the n equals 1 level, a 10.2 electron volt photon would be emitted from the atom. So here are the various levels that we saw as circular orbits in that animation of the Bohr atom, and here are the energies associated with them that we would use for problems. We'll be doing a problem in a moment. Now in Mercury, they just have the levels labeled, and again you see in electron volts the different energies that are associated with each energy level. To see how this all works, let's do this problem. What color photon is emitted by a mercury atom when an electron jumps down from level E to level B? So the place that I'm going to start is with the formula that we just learned. When an electron jumps down from one energy level to another, from a higher energy level to a lower one, the atom emits a photon. The energy of that photon is equal to the difference in energies from where the electron starts, the energy level the electron starts, to the energy level that the electron ends up at. Now in our case, this is level E would be where it starts and level B is where it finishes. So if I knew the energies of these two energy levels, if I subtract them, I will have the energy of the photon that is emitted. So I'm going to have to go to my reference tables and look up these two energies. So I go to my reference tables and I look for the energy level diagrams for mercury. Now in this problem, the electron starts in level E, so I see an E right here, and its energy is minus 3.71 electron volts. And it ends up in level B, which is down here, so that's an energy of minus 5.74. So what I have to do is record these two energies to use in my formula. So now I'm going to take those two numbers and plug them in the formula. So the energy of this photon is equal to the energy of the initial energy level, which is level E. So I had looked that up, that's minus 3.71 electron volts, minus the energy of level B, which is minus 5.74 electron volts. So I have minus 3.71 electron volts. Now I have minus a negative, so that's really plus 5.74 electron volts. So the energy of this photon is equal to 2.03 electron volts. So now I have figured out that the energy of the photon emitted by mercury when an electron jumps from level E to level B, the energy of that photon is 2.03 electron volts. But that's not what they asked me for. What they wanted to know is what color this photon would be. So how can I figure out what color this is? Well, the only information I have about colors on my reference tables is in this chart called the electromagnetic spectrum, which has all the different bands of the electromagnetic spectrum. Visible light is this narrow slice, and they've exploded out the visible light part of the electromagnetic spectrum into each of the colors. So I can see, well, if I knew what frequency, because that's what all these numbers are, frequencies, what frequency this photon is, then I could tell you what color it is. So I need to know what frequency this energy has. So I need a relationship between frequency and energy. So again, on my reference tables under modern physics, I see a formula that looks like this. E equals h times F, where E is the energy of the photon. That's what I've got. F is the frequency of the photon. That's what I want. And h is called Planck's constant, which is on the front page of the reference tables. So I'm going to solve this for frequency. So frequency equals E over h. So let's put the numbers in. So F equals the energy, 2.03 electron volts, divided by h, Planck's constant, 6.63 times 10 to the negative 34 joule seconds. And I notice there's a problem. And the only reason that I know that there's a problem is because of the units. If I didn't use units, I would never know that there's a problem here. And the problem is that I want my units of frequency to be in hertz. Hertz are 1 over seconds. So that means in all these units over here, I need for everything to cancel out, so I only end up with 1 over seconds. And that means I need electron volts and joules to cancel out. They are not, although they measure the same thing, they both measure energy, they are not the same unit. So I need to convert electron volts into joules to cancel out that joules. In other words, I need to know how many joules 2.03 electron volts is. And that means I need a conversion factor between electron volts and joules. So I look on the front page of my reference tables where I see that 1.6 times 10 to the negative 19 joules is equal to 1 electron volt. So what I want, though, is I actually want 2.03 electron volts. So I multiply 1.6 times 10 to the negative 19 joules, which is 1 electron volt, by 2.03, and I get that 3.25 times 10 to the negative 19 joules is 2.03 electron volts. In other words, I multiply this number by 2.03, so this many joules is equal to this many electron volts. And I'm going to go back and I'm going to substitute this number into my formula. Okay, so now what I have is that instead of 2.03 electron volts, I have 3.25 times 10 to the negative 19 joules. And I'm going to divide that by 6.63 times 10 to the negative 34 joule seconds. And now I can see that the joules here are going to cancel out, and I'm going to be left with 1 over seconds. So when I divide this in my calculator, I get 4.90 times 10 to the 14th per seconds, or hertz. So now I need to figure out what color that is. So now I again look at my reference tables. I look under electromagnetic spectrum. I can see I've got all the colors here. The frequency I'm looking for is 4.9 times 10 to the 14th. So notice here's pretty close. 4.9 times 10, that's 4.82 times 10 to the 14th. This is 5 times 10 to the 14th. So it seems like I'm right in here in the orange region. So the real answer to the question that they're looking for, if an electron jumps down from level E to level B in Mercury, what color photon do I get? The answer looks like it would be orange. So now it's your turn. So try this problem, and once you get an answer, show me in class. And the question is, what is the frequency and wavelength of the photon emitted when an electron jumps down from the n equals 4 to the n equals 1 energy level in hydrogen? Is this photon visible? So first of all, you might want to review the problem that I just did for you. Watch it again, and then try to use exactly the same procedure to answer this question.